So, hello everyone and a warm welcome. Today marks the beginning of our exciting 5-week journey into calculus with Python, covering weeks 8 throughout 12. Our goal over this series is not just to revisit fundamental calculus concepts like limits, derivatives, and integrals, but to understand them deeply throughout practical application using Python and critically to see why these mathematical tools are essential for cutting-edge fields like artificial intelligence and even quantum computing. But before we start, I'd like to mention that it's a friendly and inclusive space. Let's encourage each other and lift one another up. This session will be recorded. So, you might wonder why calculus for AI or even quantum. For artificial intelligence, calculus is the engine behind how many machine learning models learn. The concept of derivatives, which measure rates of change, is fundamental to optimization algorithms like gradient descent that train neural networks by minimizing errors. Understanding change probability distributions often describes using integrals, and the behavior of complex functions are all crucial in AI. And calculus provides the language for this. For quantum computing, if you're wondering why we need quantum mechanics, the physics underlying quantum computing is intrinsically mathematical and even heavily reliant on calculus. Describing the evolution of quantum states often involves differential equations. Concepts from linear algebra intertwine with calculus like vector calculus to handle quantum states and operators. Furthermore, optimization problems also arise in designing quantum algorithms. So, while these fields use advanced tools, a solid grasp of calculus fundamentals is incredibly valuable. This week 8, we start with the absolute building blocks, functions and limits. Limits are the essential concept upon which the idea of the derivative is built, making them the logical starting point for our journey. We will explore what function and limits are, visualize them using Python's matplotlib, and see why understanding this approach and behavior is so critical. So let's get started with the agenda for today. Quick function refresher, definition Python def plotting f of x, which equals x squared. We will plot several different types of common functions using Python to get familiar with their shapes, and we will look at the code. We will discuss continuous functions and look at code to visualize continuous with discontinuous types. We will see practical example linking continuity to quantum mechanics. We will introduce the core concept of limits. Also, we will cover limit notation. A limit of f of x equals L and build intuition, referencing, of course, Khan Academy. We will connect limits back to the definition of continuity. We will demonstrate estimating limits numerically with Python examples and code including sine x over x and limits at infinity. Also, we will use matplotlib to visualize some of these limits in action, providing the full code. Also, we will discuss the vital significance of limits in machine learning and quantum computing, and of course, finally, summarizing. So, let's quickly recall functions. A function is essentially a rule that takes an input, x, and produces a specific output, often written as y equal f of x. In Python, we use def to define them. For example, here is the basic Python code using NumPy and matplotlib. pyplot imported as plt. We define the function f of x returning x squared using double asterisk for power. We generate x values using numpy dot linspace and calculate y underscore values. Then we use plt.plot to draw this graph, adding labels and a title. So if we run this code, we will draw the graph, adding labels and a title. Besides parabolas, we offer various function types. Let's take a look at these examples. Polynomials like x cubed minus x. Trigonometric functions, sine of x. Exponential functions, x of x. Logarithmic functions, typically the natural log. Rational functions like 1 over x or 1 divided by x. So, this code uses matplotlib subplots generated by plt.subplots to quickly visualize several common shapes. Let's explore code and point to plots. Polynomials like x cubed minus x, trigonometric functions like numpy dot sine of x, exponential functions like numpy dot x of x, logarithmic functions like numpy dot log of x, typically the natural log in numpy. Rational functions like 1 over x or 1 divided by x. The code uses numpy.nan to prevent connecting lines across the break at x equals 0. By running this code, we will see next plots. So, let's explore these plots. As you can see, polynomials showing curves, trigonometric functions showing periodic waves. And remember, we use I'm using English pronunciation sine. If, for example, Slovenian group normally pronouncing sinus, but in this course I will pronounce as sine. Exponential functions like numpy.x of x showing rapid growth. Logarithmic functions like numpy.log of x, typically the natural log, as I mentioned before in numpy, showing slow growth defined only for positive x. And rational functions like 1 divided by x, often showing asymptotes. Plotting this helps build intuition about their behavior. So, and let's visualize continuity and its opposites. A continuous function's graph is unbroken. Let's explore code for each subplot. So, plot 1 continues the function x squared. Plot 2 jump using numpy dot piecewise. We create a step function. Plot 3 whole. This represents a function like we will dive deeper on the next slide. And plot 4 for infinite. So let's explore this subplot. Plot 1 continues. The function x squared is smooth and continuous. Plot 2 jump. Using numpy dot piecewise, we create a step function where x less than 0 and x greater than or equal to 0. There's a clear jump at x equals 0. The circles clarify the function's value exactly at the jump. Plot 3 whole, we plot y equals x plus 1, but add an open red circle at the point 1, 2. This represents a function like which has a hole at x equal 1. And as a plot for infinite, we plot y equals 1 over x squared. It shoots to infinity near x equals 0, creating a vertical asymptote and infinite discontinuity. These visuals help clarify the different way continuity can fail. Let's see how continuity appears in quantum mechanics relevant to quantum computing. A common model is a particle in a potential well, representing potential energy, V of x. This code defines and plots such a well using numpy dot once like and array indexing based on absolute value of x is less than or equal to a. The plot shows v of x has sharp jumps, is discontinuous. However, the particle state is described by a wave function, sine of x, which must be continuous everywhere, even where the potential jumps. This requirement constrains the possible shapes of it and leads to specific discrete energy levels, a key quantum effect. So, function continuity is a vital concept in quantum computing foundations. Now, let's introduce the core idea of limits. Limits helps us answer a fundamental question. What happens to the output value of a function f of x? As the input value x gets closer and closer, infinitely close or arbitrarily close, meaning as close as you want to some specific point. Let's call it c. So, the crucial point here is that we are interested in the value f of x is approaching or tending towards based on the function's behavior near c. We are not necessarily asking what the value of the function is exactly at x equal c, which is simply f of x of f of c. As we will see, the function might not even be defined at c, or it might have a different value right at that point, but it can still approach a specific value. That approaching value is the limit. So, thinking of analogies. Imagine watching your car speedometer as you pull into a parking spot. As you get closer and closer to being stopped, X approaches time stopped. What speed is the speedometer approaching? F of X approaches 0. Is approaching 0. Or consider tracking an airplane's altitude as it lands. As time approaches the touchdown moment, the altitude approaches 0. Regardless of what the reading is exactly at the moment of touchdown, if there even is one. Limits capture this crucial idea of an approaching value. Mathematically, we express the limit using the notation shown. The limit of f of x as x approaches c equals L. The image on the slide breaks it down nicely, links standards for limit. X approaches C, tells us X approaches A, tells us the input's behavior. F of X is the function we are observing, and L is the value the output approaches. The value L is what the function should be at A based on nearby points. The limit only exists if the function approaches the same value L from both sides. Khan Academy offers great detail about this, and I'll share this link later. Now we can connect limits back to our idea of continuous functions, those with no breaks. Limits provide the formal mathematical definition of what it means for a function f to be continuous at a specific point x equals c. A function f is said to be continuous at the point x equals c if and only if all three of the following conditions are met. First, the function must actually be defined as a point x equals c. That is, f of c must exist as a finite number. This condition immediately tells us that functions which hold or vertical asymptotes at x equals c cannot be continuous there. Second, the limit of the function as x approaches c must exist. As we discussed, the function f of x must approach the same single finite value a as x gets close to c from both the left side and the right side. So, the limit of f of x as x approaches c must exist. This rules out functions with jumps at x equals c because the approaches different varies from the left and right. And third, at this ties it all together, the values the function approaches must be exactly equal to the function's actual value right at that point f of c. So the third condition is that the limit of f of x as x approaches c must equal f of c. Think back to our discontinuity plots. The function with the whole failed condition 1 or 3 if the whole was defined elsewhere. The function with the charm field condition 2. The function with the asymptote failed condition 1. Only when all three conditions hold true, the function exists at the point, the limit exists at the point, and those two values are the same. Do we say the function is continuous at that point? In simple terms, for a continuous function, the function's actual path goes exactly where its nearby path suggests it should go. So, we can estimate limits numerically by plugging in values close to the target point. Let's estimate the limit as x approaches 1 of the quantity x squared minus 1 divided by the quantity x minus 1. Algebraically, we expect L equal to. The code defines f of x handling x equal 1 with numpy dot none if checks values approaching 1. The colon dot for f formats the output. The output shows f of x approaching 2 from both sides, as you can see from left and from the right. Let's visualize the limit for f of x equals x squared minus 1 over x minus 1. So point to plot. The code uses numpy arrays. As you can see, that part where numpy dot array and matplotlib functions to visualize like plt.plot and plt.scatter, plt.xv line for vertical, and plt.xh line for horizontal to plot the line y equals x plus 1. So this shows the hole at 1, 2, and highlighting points approaching the limit. We visually confirm the function approaches 1, y equal 2 near x equal 1. The limit as x approaches 0 of sine x divided by x. The code defines g of x using numpy.sine and tests values near 0. The output shows g of x approaching 1. This example demonstrates the limit as x approaches infinity of the quantity 2, x plus 1, divided by the quantity x minus 1. The code defines h of x and plugs in large x values. The output shows h of x approaching 2. Now let's visualize the limit as x approaches 0 of sine x over x, expecting L equal 1. This code defines g of x equals sine x over x using numpy dot as array and handling the x not equal to 0 case. It uses plt.plot, plt.scatter, plt.xv line, and plt.xh line to draw the curve points near 0. the limit points as a whole, and guidelines, guide observation of plot. So the plot shows the sine of x divided by x curve approaching 1 as x approaches 0, visually confirming the limit. Why do limits matter so much for AI or quantum computing? Foundation for derivatives. The derivative f prime of x, measuring instantaneous change, is defined using the limit. F prime of x equals the limit as h approaches 0 of the quantity f of x plus h minus f of x, all divided by h. Limits are essential for defining derivatives. Optimization of gradient descent. As example, AI training minimized loss using gradient descent, which calculates the gradient vector of derivatives to update model parameters. This relies entirely on derivatives, hence limits. Activation functions. Analyzing neural network functions like sigmoid or real U requires understanding continuity and limits, which affects gradient flow during training. Convergence analysis, determining if an algorithm converges. For example, error approaches 0, uses the mathematical language of limits. And last, link to quantum computing. Derivatives defined via limits are also central to physics equations governing quantum systems, like the Schrödinger equation, which describes how quantum states evolve. Limits underpin the mathematics of change, optimization, and dynamics in both AI and quantum computing. Let's quickly summarize. Functions map inputs to outputs, and we plotted various types using Python, NumPy, Matplotlib. Continuity means no breaks. Formally, limit equal f of c. We saw visuals and the quantum computing link via wave function continuity. Limits written as limit of f of x equals L describe the value f of x approaches as x near c. We estimated them numerically and visualized them using Python. Python is a great tool for exploring these concepts with the provided code examples. Limits are fundamental to AI and quantum computing because they define derivatives essential for optimization in AI and describing dynamics in quantum physics. To help solidify these concepts, here are some practical exercises and resources for further study. First, I strongly recommend reviewing the core ideas of limits and continuity on Khan Academy using the link provided. They have excellent videos and practice problems. For hands-on Python practice, try numerically estimate a few more limits using the technique we saw with NumPy. I've suggested three examples here. One involving e to the power of x. One limit at infinity involving polynomials, and one that can be factored. See if your numerical results match what you expect. Use Matplotlib to visualize different functions. Try plotting another jump discontinuity. Plot is simple continuous functions like cosine of x to see its smoothness, and plot a function with a clear vertical asymptote like 1 over the quantity x minus 3. As an optional challenge, think about the limit definition of the derivative we saw on the last slide. Try writing a small Python function to numerically estimate a derivative using that formula. It's a great preview for where we are heading. Finally, the slide lists direct links to the main documentation for Matplotlib and NumPy, which are invaluable reference when working with these libraries, along with the Khan Academy link. Please take some time this week to practice these concepts, especially with Python implementations. And of course, I'll share a quote used in today's session. So, this brings us to the end of today's session. Thank you all for your participation. It was great to have you all here. And if you have any questions at all, don't hesitate to reach out on our community Discord channel. This session was recorded and will be available on our GDG Ahlen YouTube channel later. So if you want to review it, and you can rewatch at your convenience. I really appreciate if you could take a few minutes to fill out the post-event feedback form. Your feedback is invaluable in helping us improve and make future sessions even better. Once again, thank you for joining. See you in our next session next Sunday. Until then, keep learning, experimenting, and build with AI.